So hi everyone. So this is the work that I'll present. Was done in collaboration with Michael Scharschmidt and Eiko Jänicki in the computer laboratory at the University of Cambridge. And over there, the kind of problems we had was we developed systems. So a system is something like TensorFlow or MapReduce. And so this is this bit in the middle here. And the goal of the system is to provide a way to implement some applications, so the thing you have on top, which is probably going to run on some input data, and to let this application run on any sort of hardware, or at least a wide variety of hardware. And one of the big issues that we have when we develop these systems is that because every single time the application changes and the input data changes, the best implementation of the system is going to be very dependent on what the application is. So typically, this is solved, and I'm sure you've all done this in the past, by having some sort of configuration flags exposed to you. So you set these flags so that your application performs well in your specific context. But then tomorrow, maybe you had a cluster, and your cluster doubles in size, and suddenly your flags are no longer good. So we'd like a sort of more robust way of approaching this problem. So what are the properties of the problem? There's many dimensions. Often we have, say, 30 flags or more, and I'll consider applications which have this many. A second important thing is that, so we could consider sort of optimizing these flags. So saying, okay, we're just going to use some sort of black box optimizer, tell it the objective function is evaluating my objective function. But the objective function is also quite expensive. It's often at least 5 minutes, and it could be an hour. So these two things are quite bad, but sort of the one redeeming factor that makes it an approachable problem, and this is how we solve it, is the third bullet point here. We have an understanding of the underlying behavior. We know how the system works, and that allows us to sort of take advantage of this structure and find decent solutions in a reasonable time. So to give an example of this problem, this is something that, this is a case study that we considered, and I'll show some results for it at the end of the talk. Say we're trying to schedule a distributed, we're trying to schedule the training of a neural network in a distributed way. We have this cluster at the top. We've got multiple machines. Some have big CPUs, some have small CPUs, some have GPUs. And we're trying to say what machine is going to do what work. So what we have here in this table are sort of the parameters we're trying to optimize. Some of the machines may be workers, and this means every iteration they're going to compute some gradients. If they compute some gradients, then we must also know how many inputs they're going to compute the gradients on. This is what we see here. So this one has 10 inputs. This one has 16 inputs. And on top of that, some of the machines are going to be parameter servers. So this means we're going to synchronize the gradients every iteration so that we can proceed on with the computation. So again, the problem we're kind of trying to solve is finding an easy way to optimize the content of this in order to maximize some notion of performance. Often this will be, so here this would be minimize the time to perform one iteration of stochastic gradient descent. Okay, so one approach towards optimization, which is very popular at the moment, is Bayesian optimization. So I'll start by doing a quick introduction of Bayesian optimization. The key idea is that we're going to be building an incremental model of the objective function. So here what do we have? We have our axis x is going to be what we're trying to optimize. So we're trying to pick a value between 0 and 5, which is going to have some good performance. Y is going to be the actual values we get. And what we have in blue here is a probabilistic model. And so far, this model hasn't seen any data, so it's very uncertain about what this sort of function looks like. So because we haven't seen anything, we may probably pick a point at random. So say we pick 1. We're going to evaluate our objective function at 1. This gives us this point here. And then the third step is going to be to do inference on our model. So suddenly we tell our model, OK, so this is what we observed for input 1. Now we can repeat this procedure. So now we say 4 is a promising point. OK, so we evaluate the objective function. It's pretty poor. Perform inference. And we repeat this, and every time the way we pick this point is by being smart, by thinking, okay, so we want to find a point which is said to be promising by the model. And as we keep going, we end up converging on pretty much what the objective function looks like. I mean, at least that's what we're hoping. Something which is nice about this approach is that it's able to deal with noisy functions. So say, for example, if each of my outputs here were actually noisy outputs, I can tell that to my model, and suddenly I've got some uncertainty about it, and it's like this. The ability to deal with noise in optimization is something quite tricky, but that Bayesian optimization handles very gracefully. Okay, so this is a review of the procedure we just looked at. So we have our domain. This was the single variable x before. The Gaussian process is something which is going to predict the performance, and our objective function, which is going to give us an actual performance. And every iteration, we do 3 steps. First, we find a promising point using the Gaussian process. Second, we evaluate this point. And third, we perform inference on the model using whatever we just measured. So this, again, this has some pros. So it's very data efficient. So compared to other optimization methods, this may converge in fewer iterations. But, and also, as I said, it's able to deal with noisy observations. But the biggest issue with it, and this is something which is very well known in the literature, is that if we start going into many dimensions, so say 5 or 10 inputs, so again, we had an x here, which was a single input dimension. We may be optimizing something multidimensional. Suddenly, it becomes a lot harder for the Gaussian process to kind of look like the objective function after a small number of measurements, so in the 20 measurements. So what can we do about this? And this is going to be the contribution of this talk. Our solution is going to be to use the known structure of the problem. So we're going to say, OK, so we can't just solve all the problems at once, this kind of known as the free lunch theorem. But instead, what we're going to do is create bespoke optimizers that are good in specific settings. And that will sort of like, that will be good, say, if we have a system, we're going to create an optimizer which is good especially for this system. So this is what I'm talking about here, a structured Bayesian optimization. The idea is that we replace the Gaussian process that was here by a structured probabilistic model. And this one is going to be input by a user. And this has 2 key advantages. The first one is that, obviously, if we have a better prior of our objective function, we're going to converge quicker with less data. And the second one is also that maybe this isn't so black box, and we have many things we measure. So if I'm tuning a system, I'm usually profiling. I know what machine 1 is doing. I know what machine 2 is doing. And all of these, both machines give me some outputs. So here we see multiple arrows go back because suddenly we're able to use all of these measurements. So in the rest of this talk, I'll be talking about Probabilistic-C++, which is a probabilistic programming language. The name is named after prior work done by Brooks and some co-authors called Probabilistic-C, so it was the next step. And it's a probabilistic language which lets you express easily the kind of models that we want in the context of Bayesian optimization. OK, so there's 3 things that you may want from your model. The first one is going to be to have a good understanding, to understand the trend of the objective function after a few measurements. So say if I get a measurement that may tell me this whole region of the input space is bad, and I want to be able to know that. A second thing is to have high precision in the region of the optimum. So this is something that Gaussian processes do really well, but some other models don't do so well. And finally, the ability to use many measurements, which is what I just mentioned, so that we can converge faster. So I'm going to present 2 techniques. The first one is going to solve the first 2 problems, and the third one is going to solve the third problem. So the first technique, to both have high precision in the region of the optimum and sort of like an overall trend, is going to be to use semi-parametric models. So what we have on the top left here is a parametric model. It's just linear regression. So on the red here is our true ground truth. Green here is the points that the model has observed. And the blue line is the model. So here, this is linear regression. So although it captures the overall trend of the data, so here I knew that this was something linear, it doesn't fit all of the data points. On the right here, I have a Gaussian process, which is much better at fitting all of the data points. We can see it interpolates every single one. but it doesn't capture the overall trend, and at the end it starts going down despite it being linear. And what we have at the bottom here is a semi-parametric model. So if you're familiar with Gaussian processes, this is a Gaussian process with a linear mean function. And so all we're doing is having our linear model as before and interpolating between the model and the observed points with a Gaussian process. So we still have a GP, but we just have some more things on top. So this is how I express this model in Probabilistic-C++. So here I have an object, which is a semi-parametric model object. And I express my prior in the constructor. So because it was linear, I had two parameters, alpha and beta. And I sample both of them out of a normal distribution with mean 0 and variance 1. And we also have some GP hyperparameters that we would have to sample here, which I didn't show for clarity. And all we have to say, once we've defined our prior, is the parametric model. So that linear function is expressed here. We take a single input x, and we return alpha times x plus beta. Now, once we've defined this model, we can query it by just creating this prob engine templated on this class. And this will let us do most of the things we want. So we can observe some data. So here I observe that x equals 1, y equals 3, x equals 2, y equals 4. And then I can predict the mean response of my model based on these measurements. OK, so this was the first of two techniques which solved the two problems I mentioned. The third problem I discussed as well was how to use many measurements. And the idea is going to be quite a naive idea. Just build a directed acyclic graph of semi-parametric models. So what we're going to do is, so this is this entire thing here is our probabilistic model. And each blurb here is going to be a semi-parametric model, which is going to output a single measurable value. What's nice about this way of expressing things is that, well, A, it's very easy to express this sort of DAG. And B, it's also very easy to do inference on this, because every time I evaluate my objective function, I observe the performance at the end, but also observe these two properties. And so I can use the conditional independence to just perform inference on this semi-parametric model, that semi-parametric model separately, and that semi-parametric model. So I don't have to worry about the sort of joint inference problem because I have this conditional independence. So this is the example in the context of the neural network case study. So what we have is some machine models, these semi-parametric models, which are going to predict the time each machine is going to take to execute its workload. And then what we're saying is, well, we know that all of the machines are going to work together, and then there's going to be, the bottleneck is going to be the slowest machine. So this is where we have a max here. So we have our 4 times taken, and we have max. And then we know there's also some communication issues, so we're also going to have a communication model, which is going to take as input this max and predict the time. And this lets us, again, do inference in quite an easy way and is expressible in quite an easy way. So this is how I implement this DAG in Probabilistic-C++. And again, it's quite simple. So there's quite a few lines of code here. But so if you look at the bottom here, these are the semi-parametric models I have. I have 3 of them because I'm just looking at 2 machines and 1 communication model. And here, I ask machine 1, how long do you think you're going to take? I ask machine 2 the same thing. Then I look at the max time, which is the max between these 2 inputs. So the max between M1 time and M2 time goes here. And finally, I look at the total time. And so every time you can see, here I was asking the model of machine 1, here I was asking the model of machine 2, and now I'm asking the communication model what it thinks about the output. OK, so I'll conclude on some results. So the first thing we tried is to optimize some parameters of the Java virtual machine. So we only tried to tune 3 parameters of a database to minimize the tail latency. And what we saw is, so here we had the corresponding model. There were only 3 parameters. So this is something on which we expect Bayesian optimization does decently. And we saw that these were some sort of, so in green we have the default parameters, and in purple we have the parameters that we had optimized for workload A, and here these are the parameters that we had optimized for workload B. And we see that every time we've decreased the 99th percentile latency significantly. And so this was sort of compared with a one-size-fits-all solution. What about when we compare to other optimizers? Do we converge faster? Well, yeah, we converge faster. We converge in pretty much 2 iterations here. But other optimizers don't converge that slowly either. Spearmint had converged in 16 iteration-ish. So what about if we look at a bigger problem? So this is the slide you saw before about the neural network model. And so we ran this experiment with 10 machines on Amazon EC2. And what we saw was that here, because this was so highly dimensional, other optimizers completely failed to converge. It was really hard to find one very efficient implementation. In comparison, our informed bespoke optimizer converges in just a few iterations and consistently. So to conclude, it's important to note that the result tells us that better priors in Bayesian optimization gives us some huge improvements, and we should be conscious of this and consider when do we have knowledge that we can and structure that we can exploit. Probabilistic-C++, I introduced a few concepts of, is a language to express these better priors, and it was engineered to be well suited so that both it's suited to Bayesian optimization and it's easy to express the kind of priors we want in this context. And finally, we have a paper which is going to be published about this next week. And thank you very much.
Thanks. We have time for some questions while the next speaker sets up.
One of your requirements that you would love your optimizer to be able to eat lots of data. Gaussian process, as many measurements as you would like, right? In how far have you addressed that issue? Because you're still using a Gaussian process, and those inherently are difficult to scale.
That's a really good question. So in some contexts, we're fine, because we have multiple models, and each of them receives a single measurement per iteration. So as long as we have, say, less than 100 iterations, we're definitely going to be fine, and that's not going to be an issue. One thing that could happen is maybe I have a single model which predicts, which can make multiple measurements per iteration. And that has happened in practice. In my experience, when I had this issue, I sort of devised a sort of treat Gaussian process model, which scales much better. So we have, at the leaves, you have some GPs, and the data is split along the dimensions. But it's definitely an issue that we should be conscious of. Does that answer your question? Okay, thank you very much.
Okay.